Good morning, and as always,
Slow is smooth, smooth is fast.
so scientific notation. You use this in chemistry when you're talking about the mole. It's really a way to talk about really either really big numbers or really small numbers.
Yeah, it helps us take stuff that we have a hard time seeing on a day-to-day basis, like really how big is a gigabyte? Like how big is that thing? Well, it's in a way to say, well, this thing is 1 times 10 to the something bytes. It's just a way of structuring.
So, and they're actually very precise numbers because when you get something that big or something that small, the only way we can conceptualize it as people is to say, well, it's really big. Well, saying something is really big isn't very precise, but scientific notation allows us to be very clear about what we're talking about.
And this is really important. No scientist is going to say that they don't make mistakes. In fact, if you have someone that says, I made no mistake, there's no error, and that's our fancy word, I made no error, they're really not thinking scientifically. Because at this point, we understand that there is no measurement that's 100% perfect, accurate, completely spot on.
And so to look at that, it's fine to make those mistakes. But really what we have to understand is that since everything has error, we have to account for that the best that we can.
Yeah, and so again, error, it's not a bad thing, we all do it, but ignoring error is. When we ignore the mistakes, then we're moving away from scientific accuracy, and we're moving more towards, whatever.
The way that we look at this to know how accurate a measurement is how many significant figures that you can actually measure. So when someone talks about atomical clock, that it's actually measuring very precisely, they're really just extending the number of significant figures that they have to measure that thing. When you talk about when scales that you use in the chemistry classroom get more precise, they add more zeros after the decimal, and as with that is a cost associated with that, because as they get more precise, they get more significant figures, and with more significant figures requires more time to make that measurement.
Now, understand this, that we don't just add significant figures. We don't just say, oh, I want this to be really accurate, so my mass is 52.38726 kilograms. If I don't have a device that can measure that accurate, I don't just add numbers. We typically add only one significant figure past how accurate our device can get.
So let's look at some examples using scientific notation, and we'll talk about the significant figures of these measurements as well.
So really, when we talk about scientific notation, we always look at a number between 1 and 10. You're not going to have a number that's in scientific notation that is 0.18 or 18.32. That when we talk about true scientific notation, it's 1 point something all the way to 9 point something.
So the way that looks is that we can take a really simple number, and yes, we know you can count up to 1,230, but we're using this as an example. And what we're going to say is that we're going to end up moving that decimal 3 times to the left. So our number is going to be so we're going to move it 3 times. So it's going to be 1.23 times 10 to the third, because we moved the decimal 3 times.
And all that is 10 to the third is 1,000. So think about it. If we take 1.23 and multiply it by 1,000, we get 1,230.
And we said this works for big numbers as well as small numbers. So if we're going to do it the other way, we can count how many times we move the decimal to the right, and then we still move it 3 times. We're moving the other direction, a smaller direction. So it's going to be equal to 1.23 times 10 to the negative 3.
So, and again, 10 to the negative 3 is like dividing by 1,000, 1 over 1,000. We can do the same thing. 1.23 times 1 over 1,000 is 1.23 divided by 1,000, 0.00123.
Really, the way that I always remember it is if you have a scientific notation with a negative number, it should be small. It should be less than 1. If you have a scientific notation with a number greater than 0, the number should be larger than 0.
Yeah. Now, you guys are already using this. And let's go back to our units. Remember we talked about cents and dollars? Well, a penny, 1 cent, is just 1 times 10 to the negative $2. That's all it is. And $1 is just 1 times 10 to the 2 pennies. So again, you've been doing this for the majority of your life. We're just kind of giving you a language to apply it to this course.